Quantization noise is not the only effect that we need to worry about when we implement filters in fixed point. So in general, also the coefficients that we use in our multiplications will need to be quantized to fit within our number representation that we use internally within the circuit. And this will typically cause a deviation of the true impulse response or the frequency response or transfer function of the system when we use the quantized coefficients in place of coefficients that we obtain from our design. So this can be partially alleviated by considering how we implement the circuit. So it will turn out that different implementations will have different sensitivity to this quantization of the coefficients or to the quantization effects which arise when we quantize the coefficients. So in this video we'll consider AR circuits and moving average FIR circuits, and then consider more general circuits in the next video, where we also do a more thorough analysis of how this sensitivity is affected by our choice of implementation. In order to get an intuitive understanding of the effect that quantizing the coefficients will have, let's consider this simple AR2 circuits where we are to quantize A1 and A2, the coefficients in the multiplications. And we have the transfer function of this system. So the object of interest is to see how is this transfer function affected by the quantization of these coefficients. So in this particular example, we quantize the coefficients A1 and A2 using 3 + 1 bit signed magnitude representation. So that's 3 bits for the magnitude and 1 bit carrying the sign. So since only a finite number of numbers can be represented using these 4 bits in total, that will also limit the set of filters that we can realize using this representation and this structure. So if we look at the poles that are possible for this system, they are plotted here as crosses. So every cross in the first quadrant of the complex plane here shows a possible pole position. So what we can see immediately is that we don't have any poles in this region, which is of course a problem if we want to design filters with poles in this region. Now this is mainly an artifact of the fact that we limited A1 to be in the range -1 to 1. So it turns out that if we want to place poles in this region here, we need to allow for A1s which are larger than 1. But that can simply be handled by, instead of quantizing the range -1 to 1 using the 3 + 1 bit signed magnitude representation, we can instead quantize the region -2 to 2. So making that change, we're able to fill the positive quadrant with poles more efficiently. But still, what we see is that only certain positions in the complex planes are possible. So if we were to place a pole, wanted to place a pole here, that's not possible within the signed 3 + 1 bit magnitude representation. And in particular, we have a fairly large area here where it's simply impossible to place poles using this implementation with this number representation system. So one option that we could have is simply to increase the resolution of our coefficients and increase the resolution in which we implement the fixed point circuit. So doing that will of course give us more possibilities for placing the poles. But we'll still see that even if we increase the number of bits here, it's still hard to place poles close to the real axis but not on the real axis. So we have a large area here which is largely unpopulated by poles. So one way of addressing this would be to choose another implementation. So in this case, we can see that this filter implementation, we can realize the same transfer functions using another implementation structure. So in this particular case, this is called a lattice structure, and where we have coefficients K1, which appears here and here, and K2. And this implements the following transfer function, and we can see that by choosing K1 and K2 appropriately, we can get the same transfer function as we did for the original AR2 system. So one of the benefits and one of the reasons why people are interested in lattice filters is that you can show that these filters are always going to be stable if the coefficients K1 and K2 have a magnitude which is strictly less than 1. So looking at the possible pole placements for the lattice filter, we can see that if you use the same number of bits to represent each of these coefficients, we're at liberty of placing the poles slightly more densely than for the original AR2 process. And we can also in some places place them closer to the real axis. And we had, as noted, the added benefit of guaranteeing stability for this circuit, given that the coefficients here are limited to this range of -1 to 1. So if we were, for instance, to implement the Butterworth or a 6th order Butterworth filter with a given cutoff frequency, one can see that the poles of the Butterworth filter lies in a circle like that. So comparing that to the possible pole placements of the lattice filter, which we had here, we see that they also fall on circuits. So it stands to reason that, for instance, using a lattice filter could give us a fairly accurate representation of a low-pass filter, which was the case of the Butterworth filter, using only quantized coefficients. We can also consider the option of splitting the second-order AR system into a cascade of two first-order AR systems. And in this case, the poles would appear explicitly on the feedback link. And as long as we ensure that this polynomial is equal to the product of these two terms, then we are realizing the same transfer function for those two systems. And this would give us added freedom to choose exactly the pole placement by controlling the poles exactly. Now, there is a problem with this type of argument, so doing this in general of splitting the second order system into two first order systems. So what could this problem be? Could it be that the two parts may potentially cancel each other and simply null out the output signal so that we don't get any output? Or is it that the poles may in general be complex valued, which means that if we choose this implementation, we would have to require complex valued computations throughout the circuits, which is generally more costly? Or is it that the stability of this system would be harder to control than the stability of the original AR2 system? Or is it simply that a system of this form is generally more sensitive to the quantization noise than the original AR2 circuit? Well, the correct answer is that for an AR2 system, the poles will in general be complex valued, or they can be complex valued, which means that these two quantities here would be complex valued quantities, which means that throughout the entire circuit we have to maintain complex valued computations, which are generally more costly than the real valued equivalents. Still, if we're intent on implementing the system using two first order systems, we could use the fact that whenever we have complex poles, for this one they occur with a conjugate symmetry, which would allow us to write the transfer function in this form, where we have split the real part and the imaginary part of the pole. And the complex valued multiplications could be implemented using only real valued multiplications, or a real valued circuit, in the following form. So this loop in here would essentially take care of the complex valued multiplication using a real valued equivalent. And then we could use the fact that we know that for a real valued input we'll have a real valued output, and therefore save this part of the circuit in this second branch here, because the imaginary part of this part would always have to be 0 due to the structure of the filter and the symmetry. So what we've done here is that we've effectively increased the number of multiplications from just 2 to effectively 5, even though we're sharing some of the coefficients in several places of the system. But at the expense of more multiplications, we could in fact control the poles exactly using this circuit. So if we look at the possible pole placements of this circuit and compare it to the previous one, what we would get is the following setup. So this circuit, by quantizing the pole positions, we could end up anywhere within this grid. So obviously, if we quantize the poles, the imaginary part and the real part, within this range -1 to 1, we could place a pole outside of the system, making the entire circuit unstable. But we could also easily control that we're placing it inside by simply considering the magnitude of the complex number made up by PR plus I pi. And what you see here is the possible pole placements for a 4 plus 1 sign magnitude representation. So this will give us a much more uniform grid of possible points and a better use of the space, at, as noted, the expense of adding more multiplication. So this is a potential implementation which would be less sensitive to quantization effects in the coefficients PR and PI in this case. So what we've seen throughout is that different implementations will allow us to place the poles in different places, and this is related to the sensitivity of the circuit when we have a particular design in mind and we try to quantize those structures. And we only looked at AR circuits in this case, but similar considerations can be made also for the zeros in an ARMA model, or the zeros and poles in the complete ARMA model. But next we'll just look at the moving average part, or the FIR filters, and see what effects quantization will have on these filter structures. So one of the main motivators for using FIR filters was that we could guarantee the linear phase property of those filters. And this can be accomplished by choosing the filters to be one of the following 4 types, which had certain symmetry or anti-symmetry properties. Now we see that because of these symmetries, if we were to quantize, say, this coefficient of a type 1 filter, the quantization effect would affect this one, which is the same coefficient as this one, in exactly the same way. So quantizing the coefficients of one of these type of filters would not actually change the type, meaning that if we quantize the coefficients, that will only generally affect the magnitude response of the system, but not the linear phase property. So the group delay of the filter or the linear phase will be the same, regardless of if we quantize or not. However, there is a secondary effect, and this is that in order to have the same transition from a passband to a stop band or vice versa for an FIR filter as compared to an IIR filter, we typically have to increase the length of the FIR filter. So therefore there are generally more coefficients in an FIR filter that we need to quantize than in a corresponding IIR filter, and this will again increase the sensitivity. So in order to get a feel for what the sensitivity of an FIR filter could be, I've implemented here a 50th order type 1 FIR low-pass filter using the window method with the Kaiser window. And here you see the magnitude response of, or the magnitude of the frequency response of these corresponding filters. So we see the pass band and we see the stop band, and we also see ripples, which are determined by the choice of window in this case. And the window, of course, also affect the transition from the pass band to the stop band. If we are now to quantize all of the coefficients of this filter to say 6 + 1 bits, what we could get as an impulse response is the following. So in this particular example, I've normalized all the signals and coefficients such that they fit within the range -1 to 1 before the quantization. So as you can see, quantizing to within 6 + 1 bit generally leads to a very poor match to the originally designed filter that we had with infinite precision, or very high precision at least. So in order to improve this, we need to significantly increase the number of bits that we use to represent the filter coefficients of this filter. So increasing to an 8 + 1 sign bit magnitude representation yields the following. So we are closer to the true response, but we're not really close. So for instance, at this frequency, we have 35 to 36 dB suppression, but with the quantized coefficients, we only maintain slightly over -25 dB suppression, or 26 to 27 perhaps. We're increasing further to 10 + 1 bits, we are coming closer, and this is starting to get acceptable. So for this particular example, getting to 10 + 1 bit could potentially fulfill our needs of coming close to the original designed response. Now, it's very hard to say as a general statement how many bits you need in order to get acceptable performance. In the classical book by Prokis and Manolakis on digital signal processing, they give some rules of thumb, also based on examples. So what they argue there is that for filters up to a length of 256 taps, typically 12 to 13 bits will be required. And they also made the comment that if the word length or if the number of bits of the digital signal processor that is used to implement the filter is less than 12 bits, or if the filter length exceeds these 256 taps, then typically it's a better idea to implement the filters as a cascade of smaller length filters. And this is based on the property that we can take the transfer function of a rational impulse response, and in particular for a moving average or FIR filter, and we can split it into a product of terms like this. So we have seen previously that using only real valued coefficients, we can implement, or we can split an impulse response in first order and second order terms. However, doing this will cause potentially a problem in that these first and second order components don't necessarily have the same structure as the overall filter. So even if this is a type 1 filter, for example, these are not necessarily of a type 1 structure because we don't have the symmetry in the coefficients that we have for the type 1. So if we were to quantize the coefficients of each of these terms in the cascade implementation of the filter, we could potentially violate the linear phase property by not maintaining the proper type of the overall filter, which is coming from the multiplication of these. However, there is a fix to that, and that would be to, instead of implementing it as a cascade of first and second order systems, we could implement it as a cascade of second and fourth order components which are constrained to be of the type 1 if we're implementing a type 1 linear filter. So that would mean that we only choose second order component and fourth order component which has this symmetry property around the center tap. Now one can show that this is indeed sufficient for implementing all type 1 linear filters using coefficients of this type. And also, due to the symmetry that we cause in these, if we were to quantize the coefficients CK1, CK0, CK1 and so on, we would still maintain the symmetry property of each component and therefore the overall linear phase property of the entire filter. A reasonable question at this stage is why we need in fact both second and fourth order components. So why aren't second order components sufficient in this case? And the reason for that is that the symmetry that we require of the coefficients limit our ability to implement general filters by causing particular constraints associated with these symmetry properties. So what particular constraint can you see in a second order component of this type where all the coefficients are real valued? So do you believe that you cannot cause an arbitrary DC gain, so a gain at frequency 0? Or is it that all of the zeros or the roots of this polynomial are necessarily real valued? Or is it that a root which is complex valued would have to lie strictly on the unit circle? Or would no longer the roots of this polynomial occur in conjugate pairs as they do in the general case? Well, the correct answer to this question is option number 3. And one way to see this is to see that the roots are not affected by a common division of all of these coefficients by some constant. So we could, without loss of generality when considering the roots, consider the case where CK0 is equal to 1. And if one takes the product of the zeros, and so you factor this into two first order components, one can see that CK0 is in fact the product of the 0 multiplied with this complex conjugate. And since we can assume this is equal to 1, that will imply that the 0 must have magnitude 1 if it is a complex valued 0. So real valued zeros can be placed in other places than on the unit circle, but not complex valued ones. And this is why we need the fourth order component. So to summarize the different type of constraints which are introduced. So we saw just for the second order component, it turns out that whenever you have a complex valued 0 or a complex valued root to this polynomial, it has to lie on the unit circle, and this causes second order factors of type 1 not to be sufficient to implement all type 1 filters. If we look at the type 4 filters, we have some constraints there as well. So in particular, if you happen to have a complex valued 0 or a complex valued root to this polynomial, it turns out that not only will its conjugate also be a root, which is a common case for all real valued polynomials, but also a mirrored version in the unit circle will also be a 0 to this polynomial. And that may seem like a constraint which would not allow us to implement every type of filter, but one can in fact show that this property will be true for any type 1 filters. So it's not a restrictive property in this case. It turns out that it's not always a good idea to split any given FIR filter into just second and fourth order components. But in general, splitting a long FIR filter into 2 or more components can generally decrease its sensitivity to filter quantization effects. So in order to illustrate that, let's consider again the case of the FIR low-pass filter designed with the Kaiser window that we considered before. So here I've split that into 2 cascade parts, so 2 consecutive FIR filter which maintain the same transfer function as the original filter, and I've quantized each of those 2 filters to 6+1 bits. So if you remember the deviation from the true impulse response obtained with 6+1 bits for the original filter, that was much larger than the one that we're seeing in this particular picture. And if we also in this case move to an 8+1 bit implementation, we are already very close to the desired impulse response. So in fact, we were actually closer to the desired impulse response in this case than we were for the 10+1 bit implementation of the original filter. And this is caused by splitting the FIR filter into 2 shorter filters. So if we again move to the 10+1 bits, which we had as the last example in the previous case, we see that we are now very, very close to the desired response. So 10+1 bits is definitely sufficient in order to implement this filter if we do it as a cascade of 2 shorter filters, which are done here. To summarize, We've seen that when implementing a filter in fixed point, we need to quantize the filter coefficients, and this will cause a deviation from the true or the desired impulse response of the infinite precision filter that we've just designed using some design methodology. So choosing the exact implementation or the exact circuit that we use to realize our transfer function will have an effect on how sensitive the overall circuit will be to this coefficient quantization, and one can choose more or less wisely in this regard. When designing FIR filters, we've seen that it's relatively easy to maintain the linear phase property by simply requiring that each component filter belongs to one of these 4 different types of FIR filters for which the linear phase property is guaranteed. And in the next video, we'll consider a slightly more detailed sensitivity analysis which can be used in order to guide our choice of filters when choosing an implementation with low sensitivity to coefficient quantization.